Today we will discuss about refraction of light, okay, which is about a curved surfaces we are taking. As I said, refraction of light is nothing but when the light ray is going from one medium to another medium, like rarer to denser or denser to rarer, always there is a change in the speed of light is there. That change in the speed causes the light ray to change its path. This phenomenon of change of path or bending of light ray, that only we call that as refraction of light. As we already have the basics there, directly we will start about these curved surfaces now. Okay. Now, as we are discussing about the lens, okay, lens actually it is a part of a hollow glass sphere we are taking, okay, like this. Now, we are taking a hollow glass sphere. In this glass sphere, now we are cutting into a small piece, that piece, this part, okay. This we call that as a lens, okay. When you are taking the lens, if you are having like this, so that here the edges here having less thickness, whereas in the middle if you are having more thickness is present, these type of lens we call that as a convex lens. This is called convex lens, that is, okay. Now, if you are taking the lens such a way that we are taking the lens having like this, means the thickness is less in the middle, whereas the thickness is more at the edge. These type of lens we call that as a concave lens, concave lens. This is a convex lens and this is a concave lens, that is. Now, we will see about this convex lens and a concave lens refraction here, okay. When you are taking a convex lens, means like this. This is, we are taking that as glass, this side part, like this, and here we are having air is there, air. This is glass and this is air. Whenever there is a change in the medium occurs, let us say for example, this is the curved path, so that to our left side we are having air is present, which is taken as a rarer medium, whereas the other side, this part, here we are having glass is present, which is taken as denser medium, that is, okay. Whenever if a light ray incident on the surface, let us suppose a parallel, a straight line is coming, a ray is coming incident on the surface here, as depending on the curved surface, here we are having a normal like this. Now, as we see, as the light ray is starting from air here, which is acting like a rarer medium, that is, but once it enter into the glass, let us suppose the other side, to the right side we are having, if it is a glass, where glass is a denser medium, that is, this is a denser medium, that is. Actually, as the light ray is coming from rarer to denser, always what happens there is the light ray bends towards the normal. For this curved surface, this is the normal, these dotted lines we represent with the normal. Now, these dotted lines as it is normal and the light ray bends towards the normal like this, okay. If we assume this is the glass, okay. And now, as the light rays enter into the glass, next if the light ray is passing from this glass to the other side, let us suppose like this, this is the convex surface. Now, let us suppose the light ray is coming from the glass and coming out back to the air, this is the air, and here inside we are having glass, this is the part of the glass. If the light ray is coming from the glass like this, and this is the normal. Now, the light ray appears to be bending towards the normal or away from the normal, as it is of denser to rarer, because glass is a denser and air is a rarer medium, that is. As it is coming from denser to rarer, actually here the light ray bends away from the normal here. Instead of going straight, now the light ray bends away from the normal like this. Here in this case, it bends towards the normal. and here it is bending away from the normal. Okay. This is the nature of convex lens if the light ray passes through a convex lens. And in the same way, if you are taking a concave lens, means having more thickness at the edge and having less thickness in the middle, like this. Okay. Now, in this case, if the light ray is coming like this, let us suppose. Now, the light ray is coming onto this surface like this. Let us assume this is air which is of denser medium. Now, it is entering into the glass medium which is of, that is a denser medium, that is, sorry, this is the rarer medium, and here glass which is of denser medium, it is entering. Okay. And the normal here you can take for this curved surface like this. As it is coming from rarer to denser, again the light ray bends towards the normal, means the light ray passes like this for this case. Okay. Now, if the light ray is started from the glass and if it is going back into the air, then in that case how it takes place is like this. Let us suppose this is the glass and here it is coming back to the air, which is a rarer medium here, and this is the denser medium. Okay. Now, as the light ray is coming from the glass like this. Now, here the normal is for this curved surface like this. As it is coming from denser to rarer, now the light ray is bending away from the normal like this. Okay, have understood now? So, in case of coming from rarer to denser, it bends towards the normal, whereas in case of denser to rarer, it is bending away from the normal like this. This is the refraction effect in case of concave lens, that is. Okay. Now, for activity purpose, most of the cases we are using not simply a lens convex or concave, we are using here a double convex or a double concave lens, that is. So, which means here on both the sides we are taking the same nature of lens like this. This is called a double concave and double convex lens. This is double convex and double concave means like this. This is double concave. Okay. As I said before here, always if the edges are thin and at the middle, if you are having more thickness is present, these type of lens we call that as convex lens, that is. Whenever if you are having in the middle less thickness and at the edge having more thickness, these type of lens we call that as concave. As we are having both the sides, we are having the concave nature is present, that is why it is called as a double concave, and this is called double convex. Okay. Now, we will see how the convex lens behaves, a double concave lens and a double convex lens behaves during refraction effect. Okay. At first, if you are taking a convex lens, which is a double convex lens we are taking. Now, first we are having the light ray is coming from rarer to denser, started from air. Let us suppose here we are having the glass medium here, and after that again we are having that lens, means here air medium and the light ray is coming back to the air medium like this. Okay. Now, as we already know that whenever the light ray is coming from air to the glass, now the light ray is bending. If this is the normal, now the light ray bends towards the normal like this. Okay. Now, if the light ray which enter here, which is coming from glass back to the air, which means from denser medium to rarer medium, this is denser, this is rarer, and again back to the air. This is again a rarer medium. If the light ray is coming from denser to rarer medium, means now the light ray is coming down here like this. Now again if you are taking the normal here for this surface, now the light ray bends away from the normal like this. If you observe here, the light ray which is started here in a straight line like this, now it is bending towards the normal in the first case and away from the normal in the second case. And in the same way, if you are taking another light ray starting from down here like this. Now for this surface, this is going to be the normal. Now the light ray bends, it is off towards the normal. So means the light ray passes like this. Now again if you are taking that light ray to incident on the second surface like this, now it bends as this is the normal away from the normal, like this it passes. So on combined if you see, as the two light rays which are entering onto the convex surface, which is a double convex surface, at last after the light rays are coming outside back to the rarer medium air, we can see that the light rays are converging to a point. So from this it is very clear that convex lens forms a convergent beam of light rays. Okay? So convex surface or a convex lens is having a converging nature. So whenever you are taking a parallel beam of light rays onto a convex lens, after refraction, now the light rays are going to meet at a point. This only we call that as converging nature of the convex lens. If you draw the diagram combined here like this, I am taking two light rays, one starting from the top, one from the bottom. Both the light rays after refraction, as both are bending downwards, the first one like this, and the second one, the light ray which is going up here, which is moving away from its normal, means like this, like this. Okay? This is the converging nature of the double convex lens. Okay? And in the same way, if you are taking for the case of a concave lens nature, if you see a double concave, okay, means like this, two surfaces. This is a double concave lens, and again just like the previous one, here we are having air and this is glass and coming back to air here. And we know that here already the thickness is more at the edge and thickness is less in the middle. This you call that as a double concave lens, I said. Okay. Now first case, if you are taking the refraction when the light ray is going from air to the glass medium, say for example like this. Okay. And now again just like the previous case, now we are taking a light ray which entering like this. Okay. Now as this is the curved surface of which the light ray started from air going back to the glass, now here the normal we are taking. For this case, for this point, the normal is like this. Okay. Now if it is the normal, now the light ray bends towards the normal. So means slightly deviated like this, going up there, because towards the normal direction. Okay. Now here if you are taking the second surface like this, of which now the light ray is coming from glass back to the air here like this, which is from air is acting like rarer, glass like denser, and again back to the air which is the rarer medium. That is, when the light ray enters here back onto the second surface, again if you are taking the normal like this, now the light ray bends away from the normal, means the light ray goes upwards like this. Okay. Now in the same way, if you are taking another light ray which is coming from down like this, then if you are considering in this case, how about the normal? Normal for this point of incidence is here we are having the normal, and again the light ray is bending towards the normal down here like this. Now whenever it enters onto the second one, which is about the second surface here, so air to glass is over. Now we are taking glass to air, which is taken as a denser to rarer medium, At this point again, if you are taking the normal, here the normal is like this. As the normal is like that, here the light ray bends away from the normal, means going down here like this. Okay, this is the refraction takes place in case of a double convex lens. If you observe, if I focus at two light rays which are parallel to each other, after refraction is over, of which air to glass refraction and glass to air refraction here, after that light ray coming back to the air, both the light rays are moving away from each other. Okay, both the light rays are moving away from each other. This is like a diverging beam, that is. So, if you draw the diagram, then it appears to be like this. A double concave lens, and here now we are taking two parallel light rays, one coming from the top, one from the bottom. After refraction, now the light ray is moving away there first case, and second case now going away here like this. So, this is like a converging beam for the case of double convex, whereas in case of double concave, now the light ray is moving away from each other, the light rays after refraction. So, means these two light rays are appears to be meet at a point, that only we call that as focus. This you already know, like this. So, from this it is clear that convex lens is having a real focus, concave lens is having a virtual focus, that is. Okay. Now, we will see about some of the important definitions for this lens. Okay. You can take a convex lens or you can take a concave lens, any of that you can take. Okay. The first important one is, just like the previous case like spherical mirrors, here also we are having for the lens a midpoint. Okay. That geometrical center or the midpoint of the lens, this point, this we call that as center of optic center or the center of the lens, this point, this is called O. Or if you are taking a double concave, okay, this point, this is called as O, optic center, that is. Okay. Now, next one is, if you are taking these both the lens, okay, both the lens are part of a glass sphere. So, which means, for example, if you are taking the concave lens, convex lens here, a double convex lens, it is taken from a sphere, and this one also is taken from a sphere, like this. Those are parts of a glass sphere only. Okay. Now, if you imagine this glass sphere of which our lens is a part, the center of that sphere, this part, or the center of this one, okay, this is C1, let it be, this is C2. C1 means center of curvature for the first curved surface, and C2 means center of curvature for the second surface, that is. Okay. This is called center of curvature. So, first point is optic center, of which that is the midpoint or the geometric center of the convex or a concave lens, that is. And next one we are having center of curvature, which is the center of curvature. Okay. Center of curvature. Okay. Which means that is the center of the spherical glass, of which our lens is a part of that one. Okay. Center of curvature. Now, next one, if you are taking an imaginary line which is passing through center of curvatures C1 and C2, and not only that, it also passes through the optic center. Okay. This is for convex. Okay. And the same way, if you want, even you can take for the case of concave also here. If this is a double concave there, and for this curved surface taken from a sphere, and this curved surface also taken from a sphere, the center of this one C2 and C1 like this. Now, the line joining that C2 and C1 like this. Okay. This one we call that as principal axis. This is called principal axis. Okay. Now, we got the optic center and center of curvature and this principal axis. Okay. The next one, now we will see the distances there, the next important one. Okay. When you are taking the lens here, a convex or a concave lens, the distance from this optic center to the center of curvature, let us suppose this is C1 and C2 if you are taking, this is C1 and this side we are having C2, then the distance from this optic center to this center of curvature, we call that as radius of curvature, that is called as radius of curvature. The distance between the optic center and the center of curvature is called radius of curvature, that is. As we are having two center of curvatures are there, then we are having two radius of curvatures are present, R1 and R2, that is. Okay. That we call that as radius of curvature. It is called as radius of curvature, that is. Okay. And the next one we have, that is of focus or principal focus, that is. Focus means whenever if you are taking any of the lens, a convex or a concave lens, okay, like this. When you are taking a parallel beam of light rays, if the incident on this convex lens, after refraction, now the light rays are going to meet at a point like this. This we call that as focus F, or it is also called as focal point. This is called as focus. As it is forming on the principal axis, as this is our principal axis, this we call that as principal focus. That is called as principal focus, because this focus is forming on the principal axis. Okay. And the same way if you are taking for the case of concave lens, a double concave lens like this. This is our O. Now the light rays are coming parallel to each other like this. Then after refraction, now the light rays are deviating away from each other like this. Now both the light rays which are deviating away from each other, both are now appears to meet at a point, that is called as focus. Okay. If you are taking light rays this side, you are getting focus on this side, and in the same way we are having the focus is present even on the other side also. Let it be, this is F1, this is F2, and in the same way this is F1. If the light rays you are taking from that side, then it is taken as F2, that is. Okay. This is called principal focus. Principal focus represent with F. Okay. And the next one we have about the focal length, okay, which is the distance. Focal length, small f. Focal length is nothing but the distance between the optic center and the focus, principal focus. Okay. The distance between optic center and the principal focus. This we call that as focal length. And for the case of concave lens, if you are taking, this is actually from here to here like this. This is focal length F. You can also take this one also as F. This is for F1, this is for F2, that is the focal length here. Okay. And if you see, as this is a diverging one, we have to take this as F1 and this as F2, because these are virtual focus are present. Okay. Now that is the focal length we got. Okay, and the next one is, now we got the optic center, center of curvature, principal axis, radius of curvature, principal focus and focal length, that is. Okay, optic center is the geometrical center of the given lens there. Center of curvature is nothing but the center of the imaginary sphere of which our lens is a part of that. Principal axis, that is nothing but the line passing through the center of curvatures and the optic center, and radius of curvature, that is the distance between the center of curvature and optic center, and principal focus, that is nothing but the distance from optic center you are taking. Okay, so that you are taking the light rays, whether it is converging to a point or appears to be converging to a point. That point we call that as principal focus, and focal length is the distance from optic center to the principal focus. That is called as focal length. Now by using all these basic definitions, now we are going to explain the refraction through the convex lens, which means how the light ray behaves once it enter onto the convex lens here. Okay. Now we are taking for a convex lens. Refraction through spherical lens. You can take a convex or you can take a concave. Now here I am taking a convex lens. Okay. Now if any light ray you choose, if it is passing parallel to the principal axis like this. Okay. If the light ray passes parallel to the principal axis, after refraction, and the light ray passes through principal focus. Okay, like this. After refraction, the light ray passes through the principal focus. And if you are taking a concave lens here, a double concave lens like this. Okay. After refraction like this. Now we are taking again a straight line passing parallel to the principal axis. Now after refraction, now the light ray appears to be passed through focus. The light ray appears to be passed through focus, that is. Okay. This is the first one we have, first important rule. Now the second one, if you are taking, which means now we are taking the light ray if it passes through focus like this. If the light ray passes through any one of the focus, after refraction, what happens there is the light ray passes parallel to the principal axis like this. Okay, and this is the optic center again. Okay, but if you are taking a double concave lens like this, then after refraction, then what happens there is the light ray passes again parallel to the principal axis. Okay, like this. This is for the case of convex and this is for the case of concave lens, that is. Okay. And the next one, that is the second one, and the third one, if you see, this is the second one. Okay, once again we will see the refraction through the spherical lens here. Okay, as we already got those definitions, which is of first one, the optic center, which is taken as the geometrical center of the given lens or the midpoint of the lens, and the next one we are having, next one, center of curvature. Actually, this is the geometric center. Now, this is center of curvature, center of curvature. Center of curvature is nothing but the center of imaginary lens, imaginary sphere we are taking, okay, which is a part of the lens, that is. Okay. So, center of curvature is the imaginary sphere's center of which our lens is a part of that one. And the next one we are having principal axis. which is nothing but an imaginary line passing through this center of curvatures and optic center, and after that we are having principal focus. Means when a parallel beam of light rays, when the incident on the lens here, after refraction all the light rays are going to meet at a point or appears to meet at a point, that only we call that as the principal focus. Okay, and after that we have center of curvature, radius of curvature. Radius of curvature. Radius of curvature, that is nothing but the distance between the center of curvature to the optic center, that is called as radius of curvature. And the next one is focal length. Focal length is the distance between the optic center and the principal focus, that only we call that as focal length. Now, while taking all these 6 basic definitions, now we are going to explain about the behavior of the light ray whenever it incident on any of the spherical lens here. Let us suppose first we are taking a convex lens, or you can take even a concave lens also, like this. Okay. In the first case, now we are seeing how the light ray behaves whenever if the light ray passes parallel to the principal axis, like this. If the light ray is coming parallel to our principal axis, after refraction, now the light ray passes through the principal focus, like this. Okay. In the same way, if you are taking the light ray when it passes through the case of concave lens, and again this is the principal axis here, now the light ray is coming onto the focus. But actually the problem with this concave lens is it is having a virtual focus is present. So that is why here the light ray which is passing parallel to the principal axis, after refraction, actually the light ray deviate away from that, like this, diverge. But it appears to be the light ray is coming from a point, this point, like this. This is the virtual focus we have. Okay. Now, according to rule 2, okay, here we are taking the light ray going parallel and it is passing through principal focus after refraction. Now, we are taking the light ray which is passing through the focus, and after refraction, now the light ray is passing parallel to the principal axis, means for example like this. This is the focus. Now, the light ray is passing parallel to the principal axis, like this. Okay. And again, in case of concave lens, as I said, that is having a virtual focus is present. Like this. Then after refraction, now the light ray passes parallel to the principal axis, like this. Okay, as it is a virtual focus. And again this is the optic center. Okay, this is rule 2. Okay, see that again, if the light ray passes parallel to the principal axis after refraction, now the light ray is passing through principal focus. If it is the case of a concave lens, if you are taking, as the light ray is coming parallel to the principal axis after refraction, because of due to its diverging nature, now the light ray appears to be passing through principal focus, that is. Okay. And the next one here we have the second rule. If the light ray is passing through focus now, after refraction, now the light ray is passing parallel to the principal axis. Whereas in case of a concave lens, as we are having a virtual focus is present, as the light ray is coming here, which appears to be passing through focus, now the light ray after refraction passes parallel to the principal axis. If you observe these two diagrams and these two rules here, both are actually converse here. Here the light ray started parallel after refraction passing through focus. Here the light ray passes through focus after refraction, now the light ray is passing parallel to the principal axis. Okay. Now, when come to the third case, third rule, rule 3. Now, here the light ray which is passing through optic center we are taking, like this. Now, if the light ray is passing through optic center, now the light ray passes there without any deviation here. Okay, the light ray is passing through the optic center without any deviation. Even for concave lens also same. This is the optic center. Now, any light ray which is passing through that optic center, now it passes without any change in its path. It going straight there, like this. Okay. So, these are the three minimum rules we have to follow if the light ray is passing through any of the convex lens or a concave lens, that is. Okay. So, first case, light ray passes parallel to principal axis, after refraction passes through focus. Next one, light ray passing through the principal focus, after refraction passes parallel to the principal axis. And the next one, if the light ray passes through optic center, after refraction the light ray is going without any change in its path, undeviated we are getting. Okay. So, these are the rules we are following whenever the light ray is passing through refraction through this spherical lens, whether it is a convex or a concave lens, that is. Okay. Now, following those four rules, now we are going to draw the ray diagrams here. Okay. The ray diagram means nothing but how the image is formed by this convex lens or a concave lens here. If you want to draw the ray diagram, mainly we have to follow that. Make sure that when you are using the light rays, minimum 2 light rays we have to take. Okay. While drawing the ray diagram, minimum 2 light rays we have to take them, which are passing through the lens. And second one, where the light rays are meeting after the passing through the any of the lens, after the refraction, where the light rays are going to meet, that point only we call that as image position. Image position is nothing but where the light rays meet. Where the light rays meet at a point. Okay. Sometimes, just like in case of our concave lens, as it is having a virtual focus is present, here their meeting point may not exist here directly. Means we have to extend on both the sides so that they are going to meet at one point there. Okay, which means they are appears to meet at a point, they are not really meeting at a point. Okay. So, till up to their meeting we have to take the extended lights there. Okay. Next one. Okay. After getting that point where the image is formed, image position you got, now what we have to take is a perpendicular line. Take a perpendicular line from the image position to the principal axis, from image position to principal axis, image position to the principal axis. This gives you the size of the image, this gives you size of the image. Okay. So, these are the minimum 3 things we have to follow before you are drawing the ray diagram. Okay. See that again. So, every time we have to take minimum 2 light rays following the rules. Following rules. Minimum 2 light rays, that is your choice. Now, the image position we have to take where the light rays are meeting at a point. The light rays meet at a point. Okay. And the next one, we have to take a perpendicular line from the image position to the principal axis. That gives you the size of the image. Okay. So, these are the 3 minimum rules we have to follow before drawing the ray diagram, that is. Okay. Now, we will see one by one each ray diagram there. Now, the first case. Now, here we are taking every time the object is taken at far distance, slowly the object is coming closer to any of the lens. Okay. So, first we are taking for the case of a convex lens. Okay. For the case of a convex lens. Okay. Now, first position, as we are taking the object is at very far, which means that the light ray is starting from infinite, like this. Okay. Now, as we are taking, this is the principal axis and this is the optic center O. Now, we are assuming that the light rays are coming from infinite, that is, let it be, this is F and this is C. Okay. As the light rays are coming from far distance, as the light rays are coming from infinite, we have to take a parallel beam of light rays. Okay. And we already know that if you are taking a light ray parallel to the principal axis, following rule 1, after refraction, the light ray is passing through the focus or principal focus, like this. It passes through the principal focus. Okay. As the object is at infinite, as I said, all the light rays we have to take parallel to each other. We followed the rule 1. Now, we are taking rule 2, of which now the light ray is passing through the optic center, which is undeviated, means the light ray passes through principal axis we are taking. The light ray is passing through the principal axis here. After refraction, as it passes through optic center, it is undeviated here. Okay. Now, as I said in the rules there, here both the refracted light rays are meeting at a point, which is nothing but the focus. This is the meeting point there. Then, if you see the image characteristics, okay, as the light ray is coming parallel here, in this case, the image characteristics are, actually the light rays are really meeting at a point. So, that is why here the image formed is a real image. And not only that, after refraction, the image formed is exactly at the principal focus. So, the position is image formed on principal focus. Okay. And the next one here, the image size, if you see, as I said, size how to take that is, we have to take from the meeting point up to the principal axis we have to take. But here already that meeting point is on the principal axis. So, that is why here we have to take its size, which is of highly diminished, that is. And we have seen that the light rays which are started above the principal axis, after refraction the light ray is going below the principal axis, which means that the image formed is an inverted image. That is an inverted image, that is. And we already know that all real images are always inverted images only. Okay. So, image characteristics, if the object is at infinite, this is the case, object is at infinite. So, when the object is at infinite, now we are getting the image is formed in between, image is formed on the principal focus, and we are getting a real image and which is of highly diminished, and the light ray here the nature it forms is inverted image, we are getting that. Okay. Then when come to the second case, means I am bringing that a bit closer, that object here, which means after that infinite, now we are taking the object is in between infinite and C, that is, this is the convex lens, principal axis. Now we are taking object is in between infinite and center of curvature, like this. As it is not at the principal, that is not at the infinite distance, we have to show the size of the object also. Okay. Now we are taking any two light rays following the rules here. Okay. Now I am taking the rule 1, of which the light ray passing parallel to the principal axis. Then after refraction, now the light ray passes through principal focus, like this, F. Okay. Now, the second light ray we are taking, of which the light ray passes through focus or principal focus, that is, like this. Then we know that after refraction, now the light ray is passing parallel to the principal axis following rule 2, like this. Now, here we got the image. Okay. Because this is our meeting point, and we have to take the image size starting from the meeting point, take a perpendicular line to the principal axis. That gives you the image here, the size of the image. Then if you observe here the size of the image, okay, it is actually when compared to the object size, the image size is a bit smaller. Yes, that is why here the image formed is a diminished one, that is. And not only that, if you see all the light rays here meeting are really meeting at a point, and not only that, if I am taking the object above the principal axis, the image is forming below the principal axis here. So, which means if you are taking the again the image characteristics okay, of which here the image formed is a real image, and not only that, it is forming inverted image. And the next one here, the image position, actually it is formed between O and between F and C, that is, means principal focus and center of curvature, that is. And the next one, it is of diminishing size, if you see the size, but not highly diminished, that is diminishing size. Okay, like this. Now, if you come to the next case, which is about the object is taken after infinite, in between infinite and C. Now, we are taking the third case where the object is placed on the center of curvature, we are taking. Okay, object is at center of curvature, like this. Now, let us suppose this is F and this is C. Now, we are taking object is on the center of curvature. Now, we know that after refraction, if you are taking the following rule 1, the first light ray, after refraction, now the light ray passes through principal focus, like this. Another light ray we have to take passing through focus. Then after refraction, now the light ray passes parallel to the principal axis. Like this. Now, both the light rays are going to meet at a point, which is our image position. Now, if you are taking a perpendicular line from the image point to the C, that gives you the size of the image. When you are taking for the case of center of curvature, okay, we observe here the image is formed, which is a real image again. The image formed is a real image, and we know that that is a inverted image also, because object is above principal axis, then image will form below the principal axis, that is, which is inverted, that is. This is an inverted image. And not only that, the image is formed exactly on center of curvature, that is. So, formed on center of curvature. Okay. And the next one, it is of the size, which is of same size as object, that is taken as same size as object. Okay. That is about our third case, when the object is at center of curvature case there. Okay. Then gradually if we are bringing closer and closer, then our next position is object is placed in between C and F, that is. So, now we are taking the fourth case where object is placed, now where we are taking that between C and F, object is placed in between C and F, that is. Okay. Now, again if you see the object here, as it is coming a bit closer, let us suppose this is F and here we have C, and object is taken now in between C and F there, like this. Okay. Then after refraction, now the light ray passes parallel to the principal axis one. After refraction, it passes through again principal focus, and the second light ray we are taking, which is passing through F, like this. After refraction, actually it passes parallel to the principal axis there, Now this is our image position where both the light rays are meeting, and now we have to take a perpendicular line for that, like this. This is the perpendicular line, of which here we are getting the image between infinite and C, and not only that, if you see the size like this, the image size is bigger when compared to the object size, that is. So that's why here, as the light rays are really meeting at a point, the image formed is a real image, that is. And not only that, all the real images are inverted images. Okay. Now here the image position, if you see, that is forming in between C and infinite, which is beyond CV, it is forming there. So image formed between C and infinite, that is. Okay. And the next one, if you see the size here we are getting is an enlarged size, which is more than the size of object. Enlarged size means more than size of object, more than the size of object, that is. Okay. Now that is about the fourth case where the object is placed in between C and F. Now we are coming to the next case where object is placed on the focus, exactly on the principal focus, one of the very important one. Object is placed at focus. This is the principal axis. Here we have the point O. Let us suppose the focus point is at here. Now object is placed exactly on the focus, like this. Now we have to take a light ray parallel to principal axis like before, and now the light ray is passing here parallel to the principal axis, passing through the principal focus there after refraction. Now we are taking the second light ray which is passing through the optic center here, of which it is passing parallel to the principal, both the light rays, refracted rays are passing parallel to each other, because the light ray which is passing through the optic center is going there undeviated, that is. So finally both the light rays are going parallel to each other. If the refracted rays are going parallel to each other, means both the light rays are going to meet at a point called infinite, that is. Okay, because they are going like a parallel beam. So that's why here for the image characteristics we have to take the image formed is a real image, and not only that, it is an inverted image again, because all real are inverted. And next one, the image formed between, image is formed at infinite, and the size, if you see, as they are meeting at infinite here, we have to take that as a highly enlarged image, that is of a highly enlarged image. Okay, like this. These are the image characteristics if object is placed at principal focus, that is. Okay, after refraction both the light rays are going parallel to each other, that is. Okay. Now come to the next case. If we are bringing much closer the object, which is the special case we are getting in this case. Okay. Now see, object is very much closer to the lens now. Now again this is the optic center, and here we are having the focus. Now object is placed in between focus and optic center there, like this. Okay, very much closer position this one. Now again as usual, following the light ray which is passing parallel to the principal axis, after refraction the light ray passes through focus as before. Okay, and the second light ray we are taking which is passing through optic center here, means like this. Now if you see, both the light rays are appears to be like diverging, that is. So means if you extend that back side like this, now both the light rays are going to meet at a point which is before the lens, that is. So this is our image and this is our object. Okay. So for the first time here the convex lens is forming a virtual image, that is, because the light rays are not really meeting at a point. after refraction, both the refracted rays, both are going away from each other. Okay, both are going away from each other. So that's why here the light rays appears to meet at a point on the same side. So that's why here we have to take, that is of not a real image, this is taken as virtual image, that is. And not only that, all virtual images are erect images. Okay, then here the image formed as it is on the same side we are getting. So image is formed on same side of lens or on the object side. Okay, and after refraction here at the image formed is a highly magnified image we are getting. This is of highly magnified image. Highly magnified image is forming here. Okay, so these are the image characteristics for the last one here, which is in between focus and optic center, that is. So the image formed is a virtual image, and not only that, that is an erect image. Image is formed on the same side of the lens there, and here the image formed is a highly magnified image. Particularly this ray diagram, we will see that in our practical applications in microscope. Whenever if you are placing that lens, which is our lens we are taking there in the microscope, which is a convex lens we are using, if you place this convex lens very near to that, any of the bacteria or blood cells, any of that you see, the position of that is nothing but in between F and O, that is, so that we are getting a highly magnified image we are getting in that.